Heat transfer, chapter 1, lecture 4, convection and radiation. So first let's take a look at what convection is. So convection is the mode of energy transfer by moving a liquid or gas. It's combined effects of conduction and fluid motion. So the faster the fluid motion, the greater the convection of the heat transfer. So there's two types of convection. One is what's called forced convection. If the fluid is forced to flow over the surface by an external means, such as a fan or a pump or the wind, that's called forced convection. Natural convection is if the fluid is caused by buoyancy. So in other words, you have hot air rises, so you have to put something hot down, and as it heats the air up around it, the hot air will tend to rise. So that's natural convection. The law governing convection is given what's known as Newton's law of cooling. That's so Q dot, the CONV, that's convection, is equal to H, which is the convection heat transfer coefficient, times the area through which the convection heat transfer takes place, times the difference in temperature. The temperature, Ts, is the surface temperature of the object that's hot, and T with a little infinity sign, that's the temperature of the fluid sufficiently far away from the surface. So, the values of H, those are again found in a table, and so you can see different values here for, the type of convection versus what the H value is for them. Let's take a look at a couple problems here. So here we have a 2 meter long, 0.3 centimeter diameter electrical wire that extends across the room at 15 degrees C. Heat is generated in the wire as a result of resistance heating. So this is the I squared R losses. And the surface temperature is found to be 152 degrees C, but that's pretty warm. And the voltage drop in the current through the wire measured to be 60 volts and 1.5 amps respectively. So disregarding any heat loss by radiation, determine the coefficient heat transfer coefficient for the heat transfer between the outer surface of the wire and the room. So here we can calculate what the Q dot is. That's just the voltage times the current. 60 volts, 1.5 amps, 90 watts. The surface area of the wire, that's just pi d times L. So we can calculate what those values are. 0.01885 square meters. So plugging in Newton's law of cooling, the only value we don't know is H, is the H. So we can solve for H and calculate what H is. H turns out to be 34.9 watts per square meter Kelvin. So let's talk about radiation. Again, this is the energy transmitted by matter in the form of electromagnetic waves. Unlike convection and conduction, this doesn't need a medium to travel through. It can travel through vacuum, and it travels at the speed of light. So the governing law here is the Stefan Boltzmann's law. So it's given by rho times the area times the temperature to the fourth. And this rho value is the Stefan Boltzmann constant. So for what's known as a black body, this law looks like this. You put a little emissivity constant in here, the little epsilon value. So the emissivity values are given by looking up in a table, depending on what the value is. So this emissivity is a measure of how close the body is to what's known as a black body, a perfect radiator. So for a black body, the emissivity is 1, but for all the surfaces, it's between 0 and 1. Radiation also is known by what's called the absorptivity, the alpha value. That varies between 0 and 1. A black body has an alpha of 1. it's able to absorb the entire radiation on it. So for an object that's not a black body, if you have some incident flux on it, some of it's going to get reflected and some's going to get it absorbed. So if alpha times q dot gets absorbed, then 1 minus that is what gets reflected. So net radiation transfer, this is the difference between the rates of radiation emitted by the surface and what's absorbed. So again, this goes by the Stefan Boltzmann's law. You can simply calculate what those values are. So let's take a look at a problem dealing with radiation. This is radiation effect on thermal comfort. So here, this lady's standing against a wall, and the room is maintained at 22 degrees C. The inner surfaces of the walls are at an average of 10 degrees C in winter and 25 degrees C in summer. Determine the rate of radiation transfer between this person and the surrounding surfaces if the exposed surface area and the outer surface area are 1.4 cubic square meters and 30 degrees C. So here we can plug in right in the equation. The emissivity of the person is 0.95, that's in table 1.6. So you can kind of calculate what it is in winter, and you can calculate what it is in summer. It's pretty easy to calculate, actually. The epsilon and the rho values you look up, and the area is given, and the temperature difference. You just got to remember to convert these to Kelvin. All right, so that's the end of this lecture, and this finishes the Chapter 1 lecture videos. We'll start on Chapter 2 next week. Please get started with the reading and the problems. Thank you.